So now that we've seen all these measurements of evolving galaxy populations, let's see if we can tie it together in the overall star formation history of the universe. Here is a plot that's called a Madao diagram, after the first author of the paper that introduced him, Pierre Madao, and it shows the inferred production of metals or density of star formation rate as a function of redshift, as inferred from Hubble Deep Field measurements. The three sets of points and curves correspond to three different filters, and you can see that they're in reasonable agreement. The actual curves are particular galaxy evolution models that are fit to the data. The interesting thing here is that you can see that there is a peak. There is a time in the history of the universe, roughly around redshift of unity, where it seems that co-moving star formation rate over all galaxies was at its highest. And it declined since then, as it approached redshift of 0. It also seemed to have declined at higher redshifts, which you might expect would be the case. As you first build up galaxies, they get brighter and brighter, and then they fade off. Turns out a lot of this apparent decrease at high redshifts is actually due to the obscuration. But let's have a look. Now, we can measure reddenings of galaxies, and we can correct for the apparent absorption by dust. And if you do that, you plot the same diagram. This will be diagram on the upper right here. Due to Steidel and collaborators, you find out that, true enough, as you go from here to the redshift of 1, the co-moving star formation density over all galaxies increases rapidly, but then kind of stays flat all the way out to redshift of 4, maybe even higher. Now, plotting against redshift is maybe slightly misleading, because you really want to plot as a function of the look-back time history of the universe. And when you do this, then this decline after redshift of unity is actually much more gentle, but nevertheless, there is a decline. That was all for the unobscured star formation, or just mildly obscured. Now, if we add component from dusty, obscured sources, like those scuba sources, then that boosts up the total even higher. The curves shown here are models that don't seem to fit terribly well, but they do imply that there'll be a substantial component of hidden star formation contributing to the overall history. Subsequently, measurements have been obtained out to redshift of 6, where we actually have spectroscopic measurements of galaxies, and nowadays they push them to redshift of the order of 10, but those are all based on photometric redshifts. And yes, there is a decline that sets in roughly past redshift of 4 or 5, and that's the picture that we expected. At first there is nothing, then you build up galaxies, you get more and more star formation rate going on. There is a very broad maximum of that around redshift 2, plus or minus a factor of 2, and then it declines since then. So we're now in the phase of the history of the universe where it's gradually fading away. Most of the action happened when the universe was a few billion years old. We can convert these measurements into the actual build-up of the present observed stellar mass in galaxies. And here is what it looks like. It starts at high redshifts as a very small fraction. By about redshift of unity, most of the stellar mass in galaxies is already assembled and then stays roughly constant. This is very much consistent with everything else we've seen before. The more modern observations push this further out to redshift of 6, now even beyond, and the trend continues. So we start with no galaxies whatsoever, no stars, and build them up gradually. The rate of that build-up slows dramatically around redshift of unity. There is still some build-up because there is still some star formation, but we now can actually see galaxies being assembled, stars being generated in galaxies over cosmic time. So this was the direct approach to looking at galaxy evolution. We look at individual sources, measure their distances, brightness, and so on. An alternative way is to observe sky and integrate all of the energy that we get from it, actually obtain spectrum of that overall integrated cosmic background. Note, this is not the cosmic microwave background. This is the radiation due to galaxies, stars and galaxies, and also maybe active nuclei. This is a very difficult measurement to do because it's hard to get zero comparison. You're looking at an overall patch of light and comparing it to what? So this is why it took so long to do it. But nevertheless, it was done on both optical and near infrared. And the upshot is that the total integrated density of optical and infrared backgrounds, almost all of which is due to star formation, is about 100 nanowatts per meter square per second. If you have a telescope of certain collecting area, integrate some time, that will give you the amount of power collected. This turns out to be only a few percent of the energy density of cosmic microwave background. And of it, only a few percent is actually contributed to active galactic nuclei. So here is the broadband picture. This is what happens when you integrate the spectrum of the universe in optical and infrared. There are different measurements, there are upper limits. They come from ground, from space, a variety of sources. If you recall the broadband spectrum of starburst galaxy M82, it had two humps. There was black body-ish radiation from unobscured stars in the visible light, and there was black body-ish radiation from heated dust in far infrared. Well, the same now applies to the overall spectrum of the universe, if you will. And what's plotted here is a quantity that's really proportional to the energy per unit logarithmic interval. And the fact that the two peaks are roughly the same height means that approximately equal amount of all star formation ever was in unobscured and obscured systems. Let us now turn to the question of chemical evolution. As stars are made, they explode, they release chemical elements in interstellar medium, new stars are formed. Some of those are expelled in intergalactic gas, fresh gas comes in. All that contributes to the overall chemical evolution of galaxies. How is their metallicity changing as a function of time? And here is a rough schematic diagram. You begin, of course, with hydrogen and helium and nothing else. The stars cook up heavy elements. Some of those are recycled into new stars, some are expelled out, fresh material comes in, and so on. Oftentimes, these extremely complex processes are simplified. For example, a galaxy is put all in a box and there is no inflow or outflow. Or it's assumed that the moment stars explode, that material is immediately recycled in new stars. Those are crude approximations, but they give us at least some insight of what's going on. Another schematic diagram, which conveys more or less the same story, is shown here, but you may want to look at it and find it a little more informative as to all the different connections between different processes and components are. Now, starbursts like that one in M82 can drive galactic winds that expel enriched material just produced by supernovae, thanks to the kinetic energy of supernova ejecta, out in the intergalactic space. This can be modeled and it's also observed. What happens to that enriched gas is that it contributes to the overall chemical evolution of intergalactic medium, and at high redshifts it will be observable in the form of metal absorption line clouds, which we will address in the next chapter. So as you make stars, so you would make metals. The star formation history of the universe and the chemical enrichment history of the universe are tightly coupled and qualitatively should look the same. So here is essentially a Maddow plot that shows the production of metals as a function of redshift. And with modern measurements, we can look at the dependence of galaxy metallicity on mass. You expect that more massive galaxies would achieve higher metallicities because they retain more of the supernova ejecta and recycle them more effectively. And there is indeed a mass metallicity relation. It's a very noisy one. It's shown on this plot as the gray area. That's for essentially redshift of 0. And now there is a set of measurements for distant galaxies, now put in bins to make it more obvious. And we see that kind of a relationship exists already early on, which is what you expect. Regardless of the redshift, more massive galaxies will retain more of their processed material. But the overall curve is shifted down, which is again what you expect, that you have lower metallicities and they grow. They grow in galaxies of all different masses, and at every redshift there is this dependence that is generically expected. Which will lead us into the next chapter, evolution and structure of the intergalactic medium.